Hello, RISC-V Summit attendees. My name is Akira Tsukamoto. Today I'm going to talk about TEEP and SUIT on RISC-V. These are the index of the talk. I will focus on why TEEP and SUIT is good for RISC-V and how does it work for RISC-V and the current status. TEEP is abbreviation of Trusted Execution Environment Provisioning, and SUIT is abbreviation of Software Update for Internet of Things. I am going to start from explaining what is Trusted Execution Environment. It requires both hardware and software. So on the hardware, CPU must have a particular feature to provide TEE environment, and on Intel's CPU it's called Intel SGX. AMD has RISC-V. We are not really covering in today's talk, but AMD has a feature too, and ARM has a hardware feature called Trust Zone. There's two types of the Trust Zone for the Cortex-A series and Cortex-M series, and I'm only going to talk about on Cortex-A series. And RISC-V has a PMP extension, and that provides similar feature of the TE hardware. On the software side, we really need something API and SDK to make the TE application runnable on Intel, ARM, and RISC-V CPU. On Intel provides Intel SGX SDK. ARM has many different kind of the TE software, and one of the TE SDK we're using today is Opti because it's open source. And for the RISC-V, there's a project called Keystone from UC Berkeley. And what does it provide on TE is able to run trusted application, which is typically used on ARM, and Enclave is typically used on Intel or RISC-V, but both it's an application to handle critical sensitive operation. And also another thing is personalization data. In these two, we are able to provide security sensitive operations with the TE feature on the hardware and the API SDK from the software. And this is the chart from TEEP architecture draft discussed at IETF. And what is IETF is Internet Engineering Task Force, typically known as defining UDP, TCP, HTTP, many of the internet protocols. Now it's getting famous with the QUIC protocol and starting to define HTTP3. And recently was DNS over TLS, DNS over HTTP, and etc. So the reason is talking about defining TEEP at IETF is there's a TA developer, there's many devices on the internet, and there's a many vendor on the hosting trusted application, and we like to able to work between the different implementation and different vendors. It will be very good if there's a standard way to install and update trusted application and personalization data for the different devices implemented with different vendors. And this is the reason it's good to have a protocol to be defined by authorized organization. And IETF has working groups for the TEEP and SUIT already mentioned, and it also requires remote attestation procedure. It's called RAT working group, but that's going to be a little bit covered in my talk. But these three TEEP, SUIT, RATs is major discussed in the IETF. Now it's getting the fun part. So in the chart, there's a called TAM. That's the server for the TEEP. It's an abbreviation of Trusted Application Manager. In the device, in the bottom has untrusted area and trusted area. And what is trusted area and what is untrusted areas, I'm going to explain later in the slide. But first, it has three working groups, TEEP and SUIT and RATs, and all three is working on a little bit different area. So TEEP is typically, if I oversimplified, it's defining how the TAM and TEEP device operate and how the TAM and TEEP device exchange information and the protocol format. TEEP itself has three different kind of draft. TEEP architecture draft, mostly it's explaining the role of TAM, TEEP broker, app, and TEEP agent TA in the chart. And TEEP protocol draft is defining the format, what kind of message it required between the TAM and TEEP device. And the green portion is TEEP over HTTP draft is when you're sending the TEEP protocol message over the internet, it's written in TEEP over HTTP draft. It doesn't have to be HTTP, it could be HTTPS. And honestly, TEEP protocol itself, it doesn't have to be connected with internet. It could be a USB device or some in the future, but at the moment, these three combination is discussed in the TEEP. In the area of the suit, where it plays is suit explains, defines what is TA in the suit manifest. For example, class ID, device ID, versions, what kind of the TE it requires, and etc. And RAT's working group is how to remotely able to trust the device and also the TE area called the trust area in this chart remotely from the server. That's what RAT's working group is defining. And it's all going to be put together in the future. These are two drafts among many of the drafts from TEEP and SUIT. On the TEEP, the author of TEEP protocol, Hannes, Ingpei, Dave Wheeler, Dave Taylor, and me. We all work in different companies, ARM and Broadcom, Amazon, Microsoft. I work at IST. On the SUIT, main contributor is Brandon. He worked for ARM, and Hannes, Hank, and Cohen. And these are the roles for each component. There's a TAM working as a server to manage trusted application and for the devices. And devices has TEEP broker and TEEP agent as a feature to provide the TEEP. And the trusted application is paired with app and untrusted area. And what is untrusted area and what is trusted area is untrusted area is a typical Linux or Windows or general purpose operating system is running. So the user on the device is able to install, delete application freely by themselves. However, on the trusted area, it's a hidden area provided by TE hardware and TE SDK. And this chart is heavily influenced from the ARM. However, in our implementation, what we are discussing the TEEP is able to run on Intel or ARM or RISC-V. And suddenly, we're getting into very detailing how the TEEP is work on RISC-V in our implementation. Initially, we started to implementing TEEP on ARM. Opti provides Global Platform API, so it was on top of the Global Platform API. And then while we were implementing, the draft is evolving with the discussion in the working group. So the draft, the format became from JSON to CBOR. I'm going to explain how the details about CBOR in the later. And this is the entire picture of the TAM and the RISC-V device. So the RISC-V device will have trusted area protected by PMP, which is a key feature from the Keystone project. And inside it has a TEEP agent, which is providing most of the feature of the TEEP talking with TAM server. Currently, TAM is developed by Secom, and it's open source already. And implementation inside the RISC-V devices on top of the Keystone is still under development, and we would like to make it on public repository. So what is good for TEEP and SUIT? So typically it's a payment DRM and authentication usage. And another good usage is secure firmware update. And typically these features already individually implemented in the product. However, we would like to make a standard way with the TEEP and SUIT and RAT's working group with a combination with the hardware and software and making more secure way of standard way at IETF. And target devices, smartphone, IoT, edge devices. Typically IoT and edge devices called in different ways, so more intuitive way, it explains the NAS storage, edge router, Wi-Fi router, automotive infotainment unit, set-top box and surveillance camera, multifunction printer, whatever it is, it has an Ethernet connector or USB port. And also TE is adopting to the cloud server, which is on the data center. The reason behind is the many customers started to have technical assurance that the host cloud server who is running the host OS is not able to access inside the guest OS. However, this is out of the coverage of the TEEP and SUIT right now, so it's just listing as a target devices, but not particularly explaining in the slide. And this is the procedure how the TAM and TEEP device interact each other. So TEEP has a for message and query request message, query response message, update message, and success and error message. So the first TEEP device sends HTTP post packet with empty. And then TAM will send the query request, and then TEEP device will send the query response back. The reason of the first HTTP post is sent from the TEEP device to TAM is typically TEEP device is able to make it reachable with the TAM and TEEP device each other. It's much easier from initiating the connection from the device side, because oftentimes TEEP device is underneath the NAT or firewall, so from the outside, from the TAM, accessing the TEEP device initiating is a bit difficult, so making it more implementation friendly. But right now we're using HTTP post from the TEEP device. And then on the TAM is sending the update message to TEEP device with SUIT manifest included. And then the return is successful error. So what SUIT manifest does is it will describe the trusted application binary in the manifest format. The left side is exchanging what kind of the TEEP device is already installed as a trusted component, or what kind of SUIT is supported, what kind of cipher SUIT is supported on TEEP device, so TAM could interact later smoothly with the update message and success error message. And then in the right side, TAM is sending the binary to the TEEP devices and updating or installing or deleting the trusted application or personalization data in the TEEP device. We are really going to deep dive. The format of the TEEP and SUIT manifest is written in CBOR. CBOR is Concise Binary Object Representation. It's the way of the converting text format to binary. Popular format in internet right now is JSON and ASN.1. TEEP protocol message and SUIT manifest chose CBOR because it's optimized for reducing the binary size, which is more suitable for IoT or embedded devices which CPU speed or network band is limited. And the large portion in the TEEP message and also SUIT manifest consists with many examples of the CBOR. It's very important because TEEP devices, TAM servers, it's all going to be implemented in different companies. Without the example and the draft, it will be very difficult to keep the compatibility. And when implementing the devices or TAM server, interaction between TAM and TEEP device does not behave as expected. You need to debug it. And to debug it without having examples, it's difficult to debug. In the draft is one of the good way to understand CBOR. How is the CBOR used in the draft is there's another word comes out, Concise Data Definition Language, CDDL. How the CDDL is look like this in the draft. It tells the implementation or the programmer how to create the message of the TEEP message. However, just reading this, it's not easy for everybody. If you're professional with a CBOR, you're doing this for every day, it might be fine. It's always good to have how to convert CDDL to CBOR diagnostic notation. And how the CBOR diagnostic notation looks like is on the left side. It's similar in the JSON, in the text format. So if you're reading the CDDL in the draft and you're going to make a for message in the TEEP with the CBOR diagnostic notation on the left side, then just if everybody is going to be easy from watching this CDDL and able to write the left side in it, then it will be happy world, but that's not the case all the time. So we have the example converting from CDDL to CBOR diagnostic notation, and CBOR diagnostic notation is meant to be converted to the binary, which is written on the right side. So the TAM and device is able to communicate with sending this binary between them. So that's how it goes. So CDDL is in the draft, but it also has an example of a CBOR diagnostic notation for the for message, and also it has an example of the binary representation of the CBOR diagnostics notation in the draft. When the TAM or TEEP device receive binary representation of the CBOR, it's going to be converting internally to CBOR diagnostics notation and take the meaning, take the semantics, and then process the behavior as it was written in this slide and do the processing. If I a little bit go to explaining the CDDL, in the right side is in the middle it says query request. It's defining as an array or struct what kind of the member it will be put it in and what kind of the size it should be in. And if you want to make a query request in the CBOR text format, it will be in the left side. In the real world, you need to convert it to the binaries, and the binary is exchanged between the TAM and devices. In this example, supported cipher suit is equal to 1 in the query request. On the right side, it says 8101. So if 8101 is not meant to be correctly working, you could climb up in the binary from 8301 A4 144F all the way to 01. And if that binary is different, it could be having a mistake generating binary. If this portion is not a 01 and if it's negative number or 05, then you could spot on which portion is not correctly converted. Because if CBOR parsing will be implemented in TAM individually, each device individually, and not always everybody using the same library, same implementation. And the good thing to have the example in the binary and the right size is you could expect how much the value is going to have the size. For example, 01 is going to be 8101 is going to be in the middle for the cipher suit is uint dot size 4. It means not largest binary it could have a 4 byte. When the implementing device or constrained CPU, normally you allocate the buffer size before you parse it. It will give a hint how much memory you need to preserve for the parsing the next member. And this is more larger one, seed message format examples. We are trying to put 3 examples in the TEEP message. And this is the second example in a suit manifest and TEEP message. And the left side is CBOR diagnostic notation, and the right side is the one converted to the binary with a comment on it. Let me explain a little bit in the suit diagnostic notation. Suit has an envelope. The suit manifest itself is going to be signed and verified in the TEEP devices when the suit manifest is received from the TAM. So the TEEP device needs to know what kind of algorithm is going to be used for the creating suit manifest. Suit digest algorithm ID is SHA-256, and signature is using algorithm ID is -7. It's ES256 to using to verify the signature, and the payload is coming below. These are all the current status. So what's next left? There's still many things must be done. Draft is still a few portion is missing, and the other thing is implementation. All the example here coming with the TEEP message format and the CDDL and the format example in the draft is feedback from doing prototyping. So we haven't done closest support and the TEEP message protocol. And then we need to add EAT, and we need to have a little bit of a cleanup on the documentation of the implementation. And eventually we will like host on the public repository as a reference implementation, which I've been hoping for a long time and not happening yet. So that's something I'm focusing right now. Now this is the last page of the summary. We went through why we doing activity of the TEEP and SUIT at IETF and explaining overview of TEEP and SUIT and use cases of the TEEP and SUIT and how do they fit on RISC-V and current implementation status, and how the message is exchanged between TAM and the TEEP devices. Also, how the SUIT manifest is used inside the TEEP message, and how the TEEP and SUIT is expressed in CBOR, and example of the format of the TEEP and SUIT. And this is the appendix. So if you would like to more deep dive, this is the link you could go. Yes. So thank you. Hello. Yes. There's two questions on the chat already. So the first one is what kind of RTOS? Yeah, any RTOS who would like to run it on the trusted area is just welcome to port it. Some of the operating T itself does not provide any OS at the moment, but provide various minimum libc type API and crypto API. So anything to make it more easier to program. Yes, it's welcome to port the RTOS. I forgot. Yeah. There was I forgot what was the operating system name from Australia. Yeah, already ported on the Keystone project. But yes. Yes, and also the second question is, can we implement TEEP ourselves within FPGA? Yes, of course, there's no problem. In our prototyping, we're using Xilinx VC707 and VCU 118, the Kintex 7. How you pronounce it? Kintex 7? Yeah, I'm sorry. I already know the pronunciation in Japanese logo. So and it's at the moment it's working. So, and the other question is what kind of product suit the most on RISC-V with TEEP? Yeah, I definitely believe the RISC-V suit with TEEP very well with the network equipment. I mean, it doesn't have to be 5G, 6G fancy equipment. Just the home router you could see on, does it show it? It seems like it doesn't show it, but on my back Wi-Fi home router or company corporate VPN router, which require having the latest security patches update. And Okay, the last question is, where is it? Yeah, how does a suit manifest work? Yeah, I should have been put it in the slide. So there's three-way right now. Suit manifest is inside the TEEP update message, and it only has a URL where to download the binary. Then, so the TEEP device will download it separately from the URL written in the manifest, suit manifest, and then download that binary to as a trusted application or firmware update. That's one way. And the second way is suit manifest itself contains the binary. So you just verifying the signature of the suit manifest, and if the signature is okay, then the binary, you use the binary inside. That's the second way. And third way is the suit manifest is only have containing the personalization data, which is already installed in the TEEP device. So you hook up with the installed trusted application, and then use that personal data containing in the suit manifest for the trusted application. For example, personalization data could be account information for the payment, Netflix, or configuration of the your EV car. If you, yeah, upgrading the battery capacity or something. Yes, I think that's it. So thank you.